Hi, this is Chapter 9 of Applied Statistical Analysis. We're going to focus on the basics of linear regression. If you want to follow along, you can download the code for this at this website. A link will be in the description. And if you follow this link, it will give you both of the figures that we're making and the code walkthrough. I've downloaded this to somewhere that is convenient, and I've actually already loaded it into RStudio. And then also at the top of this page, you can get a link to the book that covers this. And we're in Chapter 9, which is going to be, I don't know, roughly 200 some pages in. Let me scroll down. So here we are, somewhere in Chapter 9. I want to find this because at the top of this page it says which libraries we're using. We're going to be using especially Scatterplot 3D, Manipulate, RGL, and I think some data from the Fairway package, but maybe this is not, the Fairway is probably not used till Chapter 10. Alright, so previously we've talked about how to find differences between groups, and the whole point of the linear regression method is that it lets you not just find differences between groups, but relationships between variables in a way that's a little more systematic than just regression. So if I were to plot x and y against one another, you can see that y depends on x in some way that we don't understand. Of course, it might be that x depends on y. We can't ever really tell using just statistics. But we can see that the higher x is, the higher y is. We'd like to, in regression, instead of just describing this as a correlation coefficient, we'd like to describe this as a model, and the model has in this case a line, which can be defined by a fixed point and a slope. And usually that fixed point, we use the fixed point at x equals 0, so it's called the intercept. It's where the line intercepts 0. It's mathematically convenient, but usually not appropriate. And so some have argued that instead of using that as the slope, as the intercept, we should use maybe the center as the intercept, which is a better description of sort of the middle tendency. But that makes the formula a little more difficult to work with. Anyway, we would like to build a model of this relationship that both captures this positive relationship and eventually the variability around this, so that we can draw inferences about whether new observations are likely to happen, or whether this slope is likely to really be different from 0, if this is flat or not. And so the best model for this is a line. This little function here allows us to draw a line on top of the data, and it takes x and y as data, and then a and b as the coefficients of a line. So if I run this, I can run plot me, and you can see here I've got the original data, I've got the line, which is our model, and every point here is actually the point predicted by the model for the observed point. So every point here has, if you project it down to the line, there'll be a little dot showing where the model thinks it should be. And so this looks like, oh, maybe the intercept is almost right, but that slope is too high. So maybe I'll go down a little bit, and that looks a little better. In terms of this, my RMSE went down. I could try this. I increase the slope and reduce the I increase the intercept and reduce the slope, and that gets even better. And of course, because I created the data, I know that ideally it should have a slope of 5 and an intercept of 15. And I could try that as well, see if that even gets better. x, y, 15, 5. And so that gets even slightly better than 11.25, 10.57. So this may not be the best fit line to the data, but this is the model that created it, so it's bound to be fairly good. So the process of fitting a regression is really the process of finding values, parameter values, that best describe the data. And I guess here are 4 examples from the book. If we look at this, this is what happens if we use a slope of 0. We say, well, all we're going to do is describe it as an intercept. This is sort of a null model if you're wondering if there's a slope. You pick the best flat model to describe it, and then you could compare it against a model that has both an intercept and a slope to see if you need a slope. And so you can do various things to make this better, and you can see the result of the root mean squared error. Now, another way to do this, rather than plotting it by hand, is this nice package called manipulate. And I have to take my own advice and install it. But manipulate will build a little interface that lets us play with values, and the plots will change based on that. So if I load the library and then run this, so here what I'm doing is I'm giving it plot me. I'm giving the first argument of manipulate plot me, and then I'm telling it what values I want, and so it's going to set A and B and repeatedly run manipulate whenever I change these. So what happens is this little dialog comes up. Let me clear this so I have it bigger. I'll run this again. So this dialog comes up, and I can play with this, and when I move this, it replots it. So this maybe looks right for being in the middle, but then if I change the slope, you can see it pivots on the intercept. And so maybe I'll try to get the slope right, and that looks about right. And I can move down. And so just by looking at this, my idea of sort of the best fit line, actually the slope ends up being a little higher than with the true slope, or not the true slope, but the slope that generated it was, and the intercept a little lower. I don't know if this actually looked pretty good. If we used 10.58, if we actually used 15, I can't quite, and 5, the RMSE is 10.57, so it's almost indistinguishable. So there's an area here where where the different values really don't make a big difference for the overall goodness fit of the model. All right, so this shows how to do the parameter estimation by hand, even though you may not ever really need to do that, because it gives some insights into what the slope means and what the intercept means. And what you should recognize is, for one predictor, the intercept really represents where it happens to pass through 0 on the other value. And oftentimes that's not meaningful. And so the intercept oftentimes really can't be interpreted on its own. You may have to do a transform to it. A difference between intercepts might be useful to know, but it could be ambiguous what the actual meaning of that intercept is. So we show we can estimate this by hand, but just like when you're trying to estimate any parameter from a normal distribution or something, there are statistics you can compute that estimate this directly. And these are how you can compute those for a 2-parameter model. This is the formula. And there were 100 observations in our data, and I can compute beta 1, which is going to be the intercept, and beta 2, which is going to be the slope. And I can report these, and you see, I'm sorry, I got this backwards. Here, beta 2, that's going to be the intercept, and beta 1 is going to be the slope. And even though the intercept 15.5 was what the original data had, we can find that the best model describing this has 14.05 as the intercept and 5.41 as the slope. So if I then go plot me of x and y and 14.05 and then 5.147, I think this should be better. I think maybe I have loaded these incorrectly or something. But this is going to be the best fit model using this type of formula. This is actually writing out longhand what's much maybe slightly simpler approach using linear algebra. And I won't go into the detail on this, but really what we have here is two predictors, 1 and the x value. And so if you use 1 as the predictor, all you can do is estimate a multiplier for that predictor, and that is going to be the equivalent of the intercept. But then if you use x as a predictor, then you have the slope. How much do you multiply the x value by to get the best number for the slope? And I get the same two numbers here if I do this. So this can be done to solve for more complicated 3 or 4 predictor models rather than just 2 predictor models. Well, this would only be relevant for 2 predictor models. But of course, no one ever does this because there's a linear model function in R that will do this for you. And if I type out model, it'll give me those numbers as well. So I can fit this to get the intercept and slope, and if I want to plot the best fitting line, all I need to do is hit type AB line and give it the coefficients of the model. So you can get coefficients by the function coefficients of model, and it'll I guess coef of, I spelled coefficients wrong, that was a problem. There's a CI at the end. Or I could extract it like this, and you can actually shortcut these. I could just do that to get those numbers as well. And so by typing AB line of that, I get the best fit line automatically. AB line takes 2 values, but it also will take a vector of intercept slope. Okay, a couple things about this. So we have this model, and what you often want to do is use it to make a prediction. And so if you have an x value, I could say, I have 6, what's my model's prediction about what the y value should be? And you follow this up here and you see it's going to be about 42. Well, I can do that by using the coefficients of the model. It's just going to be 14.05 plus 5.14 times whatever x value you have. I could come up with all the predictive values of the model, just like this. And this gives me, for every observation, what was the predictive value. And that's going to be wherever the closest point on this line is to the observed data. But this gives me the actual set of values. And of course, I can correlate this with the truth. So if I correlate y with predicted y, it gives me a correlation of 0.836. And if I square that, it gives me the r squared of the model. So the r squared here is 0.7. which tells me that X accounts for 70% of the variability within Y. So the but the nice thing about this is no matter how many predictors, this doesn't incorporate X anymore. So no matter how many predictors I have, I can get a measure of how good the model is. And here, 70% of the variability is pretty good. It's exactly this much. But oftentimes you will find your model has parameters that are predictive of the outcome. And then you'll look at the R squared and it'll be very low. And so this gives you a different understanding of what's going on in the model. You can get these predicted values, well, from the model itself. So model fitted values, or you can just abbreviate that to fit. This gives you the same thing. Will give you exactly the same thing that I produced right here. I can just show that by finding the correlation between the two, and it's equal to 1. But let's say you want to make a prediction about data that you don't have. If you want to make a prediction about data you don't have, like maybe I want to know what the value is here, and there's no data. I don't even have to, or what would it be for 5.5? I could use the predict function. So the predict function takes, let's look at this more carefully. It takes the model as your first argument, and then a data frame, which includes any predictors you have, as your second argument. So if I give it the data, and I say data frame x equals x, I'll name that x, then I've got one variable in this data frame called x. But it doesn't have to be real data. I could say x is equal to 1, 4.5, 9, or even 100. And those would give me other x values, so I could then predict what the model thinks the y value should be for those values. And it'll tell me for 1 it should be 24.34. It's going to be right in here. Or that's 2. For 2 it should be 24.34. For 4.5, that's around here. You'd expect to be a little less than 40, and it's 37, and so on. So the predict will give you predictions out of the model for any input values you have, not just the ones you observed, and so it can be misused. I mean, we've only observed data in this range. And we can see that, well, it doesn't look like any appear below 0. And maybe this is something where values can't be below 0. But if you extrapolated with lower values of x, maybe the model will predict that the outcome will be below 0, and that might not make any sense. And of course, you could, maybe this is, year in school or something, and overall score on an intelligence test, and it seems to be linear in this range. But if you extrapolated, well, if I spent 10 more years in school, you'll be over 100% on the test, which doesn't make sense at all either. So the model doesn't know anything about data outside the range. It just tries to best describe the data within the range. This is just another example of prediction and extrapolation. I could give a negative number or 0 or a very large number, and it's just going to give me the value of that line at that point, or if I have a more complicated model, of the combined functions of all of these. One thing, I could do, so what I had done was lm of y tilde x, and it gives me an intercept and a slope. But you don't actually have to have an intercept. You can fit a model with no intercept. If I do +0, or I could do +1, I think they both work the same. This forces your intercept to be 0, and it just estimates the slope. So there are times when you have data where you'd expect the intercept to be 0, even if you don't have data there, and so you can force it to be 0 just to be able to estimate the ratio between two things. So if you want to know the overall exchange rate between currencies, you could find how much, on 10 different occasions, how much money did I take to the exchange and how much did I get back. And if you assume the intercept is 0, then it'll give you that ratio between the two currencies. If you don't assume it's 0, then it will maybe fit an intercept, and that might help you estimate like if there's a flat fee every time. But if there's something where you're expecting there to be just a pure ratio between two things, you can force it to not fit a slope. And I guess if we plotted this on here, we could do AB line 0, 7.211, and that's the best fit line that forces the predictor to go through 0. All right, next I want to look at an alternate for estimating these parameters. So in the previous chapter, we looked at both parametric and non-parametric measures. And for a model like this, the estimating process we just looked at finds the best fit line in terms of mean square error. So you take all the predicted values and you take the deviation from the line, you square them and you add them up, and it finds a line that best minimizes that sum square. But that might not always be the thing you want, and so there are other ways you might want to, other things you might want to optimize. And a lot of these have to do with trying to fit sort of down the middle. So there's an equal number on top versus on the bottom. Now, it turns out there's a lot of ways you could fit down the middle. I could draw a line like this to fit down the middle. So that can't be the only concern. But maybe if you fit a line through the middle, for any sort of local region, it kind of splits things in half. There's several approaches to doing this, several algorithms that have been developed. Some are only applicable for intercept plus slope models, single predictor models. I'm going to show you one that's available for multiple predictors. It's called Quantile Regression. There's a library within R called QuantReg, and so make sure you install it. And it works. It works a lot like linear regression. It has RQ for regression quantile instead of LM, but the basic predictors, the basic mechanics work very similarly. So let's say I've got this data set, and I will just plot it here. That says if we look at socioeconomic status of parents in a family, and then we look at what's the income that the child ends up earning in that family. We can see if we measure socioeconomic status on 0 to 10, you can see here maybe this is child's income times 1,000 or child's income per month or something like this. The child is, as an adult. You can see that there's some that are going to be high, some that are going to be low, and in general, income is very skewed. And so if this is times 1,000, this is everyone above here are people who make a lot of money over 500,000. These are all the millionaires, and in this group, there are 2 millionaires. And there's some people with high income whose parents had low socioeconomic status, and so we're a little worried that whatever we arrive at might be highly influenced by these points. We'd like to get a better look down here. And so if I plot this again of x and y, but restrict the range with ylim, and say, I don't know, 0 to 100,000. Instead of x and y, it's SES and y. Or maybe we go up to -20 and 120. We can see that there is, in this data set, which is completely fake data because I just generated with this function, there is sort of a relationship, and even some people are below zero, which I guess might just indicate that they have no income or they're in debt or something like that. But this is highly skewed. Most of the people are around here instead of up much higher. Now, if I fit a linear model through this using exactly what we've done before, and then I do AB line of mod 1 LM, you can see that my best fit line is drawn up from the main sequence of the data. And maybe that's fine because if it's being highly influenced by people who make a lot of money, but maybe that's sort of what I want. But maybe I want to sort of model the midpoint of the data at any point. And so that's what the RQ in quantile regression, regress by quantiles will do. So you have to load the quantreg library, and now if I plot this, well, you can barely see it, but let me plot these together now. And you can see that here's the whole raw data set. And you can't even tell that there's a relationship here because it's so highly influenced by a few people who have very high income. And overall, these relationships look about the same. But what I've plotted here would be this is what the regression model comes out with. And one of these is what the quantile regression model comes out with. But I can also think about, well, I created this data myself, so I know that I know what the relationship should be. It should be have an intercept of about -12, and it should go up about 5 units for every SES. But then I add noise to this, and this noise adds a certain amount to it. And so if you look at what this noise looks like, it's got a median, and that median ends up to be about 20. So that means the best fitting model to sort of the median should be have an intercept of about 8 and a slope of about 5. And so I've plotted that here as the dark line. And you can see that this quantile regression hits exactly along where sort of the generating model is. The median of the generating model. So any slice here, the median, if you had enough data, the median would be right about here. Versus the linear model, which highly overestimates it because it's highly influenced by these huge outliers. So this quantile regression is an alternate way of estimating the parameters. We did it by hand before, and we did it with least squares criteria. This is no longer least squares. This is trying to fit it to the median point, but it's an alternative way that might be useful if you have highly skewed data, or it could come in handy to be maybe more robust if you have a few outliers, because it may not be as highly influenced by outliers as regular regression would be. Okay, so those are methods with one predictor. We can also do all this with two predictors. The quantile regression will work with multiple predictors as well, but let's see what this looks like. So now I've got two independent values, x and y, that I'm sampling randomly, and a z value, which is it's a combination of these, x and y, plus some noise. So I'm going to make a new function plot me that we'll do this. And now I've got an intercept, that's b0, and b1 is the relationship with x, and b2 is the relationship with y. So I really have two slopes, one with respect to each predictor. And those two slopes together with the intercept actually form a plane through three-dimensional space that this fits through. And I can adjust either of these, and I've plotted here x versus y and x versus z, and then y versus c. These are the two predictors. So you could, if this was folded 90 degrees out toward you, this would be a sort of a cube. Every point here corresponds to another point here, and you could visualize it that way. And this over here just shows the model's overall goodness of fit. So maybe I want to see if I start changing this slope, and that's the slope related to this. it's sometimes easiest to do these separately, so I think maybe about 5.6 would be good. But now let me look at this one independently, and I think maybe a slope about like that would be good, so 14.7. So I'm going to move this one back up to 5.6 and 14.7, and then it's going to be green if it's too high and red if it's too low, so I'm going to have to drop this down a little bit, and I can play with this. So maybe I cut about half of them there. Maybe I want this one to be a little higher or a little lower. So this might be my best guess. And if we look back at what generated this, it was a x slope of 5 and I guessed 5.4, and a y slope of 15 and I guessed 14.7, and an intercept of -12 and I guessed -13. So this isn't going to be perfect, and my correlation, or my r-squared value, is 0.957. And if I were to then try plot me 2 with x, y, z, and the actual values, which were 5, 15, and -12, look over here at our squared value. That didn't work out at all. So I did something wrong here. 5, 15, and maybe it's supposed to be +12. This is still not right. Let me try this manipulate again. And I'll set these manually to because I have these in the wrong order. The slope here, the intercept is -12. So this guy has to be -12. And this guy has to be 5. And this guy has to be 15. So here we can see we sort of split the middle, and the r-squared, or the correlation, ends up being 0.955. And yeah, that's an r-squared value. It's a squared correlation. So again, what you like to do would be to estimate the intercept and the two slopes automatically rather than having to do it by hand. And we can't use those beta 1, beta 2 formulas anymore. But now if I give a predictor of 1, x, and y, I can use this linear algebra. And this actually gives me the best fitting lines. So rather than -12, the best fitting line was -16. So let me see if I can do this again. I think I have this -16, I don't know, -16.47, 5.85, and 15.22. So here the r-squared goes up a little bit from 0.955 to 0.957. So even though the true model does pretty well, there's another model that's not true that does even better. So I can get that from this, or this is just plotting the same thing. I could estimate those directly from the LM. So if I look at this, it will tell me what these coefficients are. I can extract them with coefficients and I can plot them directly, get the same thing again. So doing multiple predictors, it treats them all as independent, and it fits the best model for all of them together. All right, so another way to think about this is as parameter recovery. So here I've created some x and y values that there's no noise involved. And I can fit a model to that and look at the model and look at the predicted model. And in fact, if I look at G1, the intercept and the slope are extracted exactly the same. Slope was 3 and intercept was 55. Or I could add noise. And here's the same thing with noise. And there's my best fit model. And so as I add noise, my parameters are going to be roughly similar to what the true parameters to generate are. It's aiming to do that by finding the ones that minimize the sum squared difference. But it's going to do the one that best fits the data, not the one that came from the actual model. So here I've overestimated the intercept and underestimated the slope a little bit. And so usually you may have trade-offs. If you get one that's too high, the other one will be too low to compensate for it. So that's more noise. We can get these parameters directly, and let's see. And this actually compares for this data set the true model and the best fitting model. So you just have to recognize that, and this is what we're going to be dealing with next semester, next chapter. The model you extract will be related to the true model, but you're sampling a slope and intercept from the truth, and so you may not be exactly correct. And then the same issues and questions as we had before will exist. Is this slope you see likely to have arisen from chance? We'd also like to think about the other assumptions of the model which involve the residuals. So this shows x and y coordinates, but I can take the difference from the line for every point, and those are called the residuals. So there's the fitted value, which is the line, and then the difference of the truth to the model are the residuals, or the residual error. And you always, especially once you want to know if your model's any good, the first thing you do is look at these residuals and see if they violate any of the assumptions you make. And so if we're trying to do any hypothesis testing, we'd probably assume that the residuals are normal. And we can look at this and say, well, that looks pretty normal. We can do a QQ norm plot, and this looks reasonably flat. You might think it sort of bends at each end a little bit. So it's maybe doesn't quite have as long of a tail as you might expect or something like that. But once you do a model, usually the first thing you're going to look at, along with a fit, is get an understanding for the residuals. Because if you want to try to make any inferences about the true data population based on the data you collected, you've got to know if your assumptions are being met. So finally, we have just a couple examples, if you have multiple predictors, of how do you actually look at this. And previously we looked at sort of two views from a two-dimensional thing, but there's a few libraries that will help. And so if you install packages of scatter plot 3D and I'll install RGL as well. I think I need to put these in. And so we're going to look at Scatterplot 3D and RGL, and then Plotly also has a version. I'm not sure if I have Plotly installed on here, but it might take a while to install. So I may have to also install it, pause my recording and install it and show what it looks like. But I guess even this one, RGL and Scatterplot 3D, are taking a lot of other packages, Shiny, Crosstalk. I think I just am reinstalling everything. Let me pause until this is finished. All right, I've installed Scatterplot 3D, RGL, and Plotly, and so we'll load each one of these when we use it. But Scatterplot 3D makes a nice 3D scatterplot, and I've got to make sure I load these right. And what I'm going to do is make a panel of these, a set of panels of these. Object G3. And Scatterplot 3D actually takes a regression model and will plot the plane related to that model. So here I've got X and Y, and I can relate them each to Z, and you can see how they're each related. But this is sort of like two-dimensional views. And you can't see it because it's kind of squished up in this, but now I've looked at it. I've changed the angle. This is the same data looking at from a number of different angles. And if I didn't, I could do the same thing, but make it a single panel, and then it's kind of an animation. So you can't quite see it here, but if I sort of rotate through the space at different angles, so you can see how they do lie sort of on this plane described by that plane, and find the best angle to visualize it under. So that's a nice one that creates kind of simple line charts for viewing, but it's hard to sort of explore. So the RGL library, it looks like this won't work without having to install other things. But the RGL library, which you can, I guess, see a screenshot in the course book, will let you dynamically sort of explore the space, which might be available on some versions of R or some platforms. And let's see, we're in chapter 9. And so it will let you drag these around. This is actually from the Plotly package, and Plotly is a nice graphing library that makes web-enabled graphics. So if you load Plotly, there's probably no reason why you'd want to use RGL if you have Plotly installed. So that's a picture of the Plotly, and I can move this around to explore it. And you can see, oh, it looks like they sort of fall on this plane. I'm not you probably can draw a plane too, but this also lets you look at different points and see the X and Y and Z coordinates and things like that. Take a screenshot, download a PNG and stuff, or you can post this on a website for people to look at. Okay, so that is it for this chapter on regression, and we covered both linear regression doing least squares estimation, estimating it by hand by looking at it, and also through other ways like quantiles, a quantile like the median. And then we also talked about um, not just using a single predictor, but multiple predictors. So far, we haven't talked anything about inference, anything about whether these slopes are statistically significant or different from zero. And in the next chapter, we're going to talk about testing the linear model. But for this chapter, we've just talked about estimating and we've covered all the basics. So stay tuned.